So I was recently working on my mill and I realized something. I don't actually know how fast it's spinning. Now, in light of this revelation, you might be objecting that it has an RPM display very prominently on the head, right under the googly eyes, and this is true. But what you need to realize is that's just a cardboard disc that spins as you adjust the CVT, and the only thing clocking it at a specific angle is that acorn nut in the middle. I know because I had to disassemble the entire head a few years back when a screw worked out and locked the brake on. And then I did it again just a few weeks ago, as I was tracking down why it had started to jump out of low gear so easily. Tip: at least on mine, the high neutral low shift lever is attached to a smooth shaft with just a clamp. No keyway or spline or even a set screw and dimple. Turns out that can slowly slip over time, meaning that I had been shifting less and less fully into low over the years without realizing it, hence the growing tendency to jump out of gear in its rather alarming way. So, boo cheap design, but also yay easy fix. Anyway, after each time it was disassembled, I had reset the RPM disc by dialing the CVT down as low as it would go, then setting the disc to its lowest setting, assuming those matched. And frankly, that was more than good enough for the non-production, non-optimized, decidedly non-professional machining that I do. I can get by without an RPM reading at all and just work by ear. But still, the thought that it could be wrong started to bug me. I needed a way to directly measure the rotational speed, obviously. I needed a tachometer. But asking that prompts another question, which opens a rabbit hole leading to the very existence of this video. What kind of tachometer? Because there are multiple, completely distinct technologies for measuring RPMs. I couldn't decide between them, so I just got one of each. And since it's still, definitely not putting in an effort yet December, I thought we could take a quick look. This is a basic, dirt-cheap digital tachometer. Aim the laser at the thing you're measuring, and it'll look for changes in reflection. It assumes it'll see one high to low or low to high transition per rotation. If the part happens to be half black and half white, that might work on its own. But just adding a stripe with Sharpie on raw metal didn't work for me. Luckily, it comes with a couple strips of retroreflective tape, which pretty much guarantee a good reading once applied. And it works great. 1620 RPMs according to it, compared to the 1400 I dialed in on the CVT. And on the lathe it's reading about 410, while the gearbox claims it should be 460. Interesting. This style of tachometer is simple, cheap, fast, and doesn't have much of a learning curve. So it's definitely the correct choice for what I need. I just can't help but think it's a little bit boring. So let's look at another kind of electronic tachometer. Flashing light warning. This is a stroboscopic tachometer. Not exactly expensive, but not dirt cheap like the optical one. This doesn't have any sensors on it, just this array of LEDs which can flash at different frequencies. You measure the rotation by manually adjusting how fast it is strobing. Shined onto something spinning, you can dial this in until it appears to stay still, like a wagon wheel in a western, rotating a full 360 between each flash. It made for some fun glitch effects in the progressive scan of my camera, but if you just focus on the part itself, the video I was able to capture is a decent representation of what using this looks like in person. On the mill it reads 1620 as well, which is giving me a lot of confidence in that reading. And with it, I could even measure the pedestal grinder, matching the nominal RPMs of the motor quite nicely. Measuring this would have been a challenge for the first device. I don't think you're going to get tape to stick to either the polisher or the wire wheel. So you'd have to remove some of the fairing to be able to see the shaft itself. The stroboscope is much more convenient. I like that this model comes with a phasing button, which slightly speeds or slows the strobe while it is being held, so you can rotate which face of the spinning part is caught in the flash. One use of these is to be able to inspect spinning parts without turning them off, so that's really useful. Since you're in charge of the strobe rate, remember that things will also stand still if the strobe frequency is 2, 3, or any other integer multiple of the rotational rate. So you've got to be careful to make sure you find the lowest frequency which works. This is a basic limitation of the technology. Really a statement of a brute fact about the universe we live in. Not, as this reviewer on Amazon seemed to think, some kind of fault with the product design. And if the thing spinning is radially symmetrical, then you have to be careful you're not catching it having only spun 120 degrees or whatever. Few things in this world are truly perfectly radially symmetrical, but you can always add a sticker or a Sharpie mark or something to break the symmetry if you're unsure. It's a bit hard to see in this video, but the Sharpie mark was plainly visible on just this blade and not the others when I phased them around. Plus, bonus, it's a rave gun. Anyway, this is a mechanical tachometer from somewhere in the middle of the last century. Rotating its input shaft causes weights inside the device to move outward through centrifugal force, like on the governor of an old steam engine. The faster it spins, the higher they lift, and the more the needle moves. There are some other mechanical tach designs which use a kind of spring-loaded friction clutch or magnetic eddy currents, but I don't think this is one of them, and it's far too nice to crack open without a really good reason. You operate it by holding it in line with the shaft whose rotation you're trying to measure, and using one of these rubberized attachments to couple the rotation. You have to set the expected range, and the manuals all warn of dire outcomes if you have it set lower than the actual speed. So, if in doubt, set it to higher to begin with and work down. For the same setting on the mill, it reads about 1540, 80 lower than the other methods. And I would definitely trust the others over this. I have no clue when it was last calibrated. I'd always seen them come with a wheel attachment like this and never understood why. Holding this up against the side of a rotating shaft will create a gearing ratio, and the amount the tachometer shaft spins would depend on the diameter of the shaft being measured. So how could this be useful for measuring RPMs? In short, it isn't. This is for using the same device to measure the linear speed of the surface of a rotating part. In this case, the wheel has a 6-inch circumference. So if you divide the value shown on the gauge by 2, you'll get the surface speed in feet per minute. Testing it on the 1/2-inch bar on the lathe, it reads about 102, so about 56 surface feet per minute. We know it's spinning at 410 RPM, according to the digital tach. So that's pi over 2 inches per revolution, or 0.13 feet, at 410 revolutions per minute, gives us 53.6 surface feet per minute. Not bad, and definitely good enough as a starting point for setting up machining operations on a lathe. The physics of a cutting tool don't really care about RPMs per se, only about the speed that material is coming at them. That means that larger diameters will need lower RPMs in order to maintain the same tangential surface speed. This is particularly obvious when looking at a facing operation on the lathe. Because the radius of the cut is constantly changing, the surface finish will be different across the face as the cutter moves in and out of its sweet spot. This can be fixed if you keep changing the speed of the lathe as the cutter moves in. Tricky to do on an acoustic lathe, but it's completely standard on modern CNC lathes, and you can hear the motor hum get higher and higher in pitch as the cutter approaches the center. Measuring rotational speed in 3 completely different ways is pretty good, particularly since I only ever really needed one, if even that many. But there was a 4th tachometer modality I really wanted to explore, and really it was the reason I got on this kick to begin with. Let's talk about vibes. See, if you're measuring RPMs, that implies something is spinning. And unless that thing is absolutely perfectly balanced, it's going to vibrate at least a bit as it spins, and maybe a whole lot. And vibrations can be measured. We just have to multiply the frequency of the vibration by 60 to turn those cycles per second into the revolutions per minute we're looking for. We could probably do this with an accelerometer, but until fairly recently those were ridiculously expensive. Plus we already decided that digital is boring, so let's keep it analog. Instead, what if we had a wire of the correct length so that it would resonate with the vibration frequency that we're interested in? Then if we start to see it whip back and forth, we know that the RPMs are generating that frequency of vibrations. And if we could move the wire in and out, we could tune it on the fly to detect whatever frequency we're interested in. I present to you the Vibratac slide rule tachometer and the Tracit cerometer, 2 different implementations of that very idea. On the Vibratac, you slide the wire in and out linearly, while on the Tracit, you rotate a spool which feeds it in and out. The Tracit is still being manufactured. I got this one new off Amazon. I think the Vibratacs might also still being made, but their website doesn't exactly invite confidence. And the listed price hasn't changed since 2017, so draw your own conclusions. Both of these take some getting used to. With the stiffer wire of the Vibratac, I failed to get a reading at all when used on electric devices around the shop. Even the grinder couldn't get a result. But the marketing material all talks about internal combustion engines, which certainly do tend to vibrate a lot more. That's one of the nasty things about them. So I tried it on the old lawnmower at the shop, and it immediately worked. The trace-it cerometer was a bit easier to get working, though it was still a bust on the smoother running mill. Don't ask me what the Cero prefix means though. I failed to find an explanation, only getting some wild-ass guesses by the Google AI. So I summoned all my introvert courage and did a basic journalism. I emailed the company and asked. Turns out, they don't know it either. It was already called that when the owner's great-grandfather bought the patent, and the explanation has been lost to history. So that's both frustrating and kind of amazing. Anyway, the thinner wire on the cerometer made it responsive to lower levels of vibration, and I was able to get a faint but definite reading on the pedestal grinder, which matches both the stroboscope reading and the 1800 RPM claimed on the motor nameplate nicely. But with both of these, it was always going to be a fairly slow, finicky process. You have to adjust the length, pause a second or two to see if it's resonating, at least on electric motors, and keep repeating until something happens or you give up. It's neat that these devices are so portable. And they're analog but almost solid state and barely having any moving parts to break. That's really cool. But it would be nice to have a whole bunch of them next to each other set to different lengths, so that at a quick glance you could see the results for a whole bunch of resonance bands. Friends, I present to you exactly that, a Fram Resonant Reed tachometer. 60 tuned rods called reeds in 200 Hz increments. These came in a variety of sizes and frequency ranges. Some are designed to be handheld, while others like this one were meant to be mounted more permanently. These aren't too hard to find, but I had been hoping to find one with a low enough frequency range that I could mount it on the lathe. This one only goes down to 1000 RPMs, which is higher than almost anything I do on the lathe, and only covers some of the high range on the mill. But now that I actually have one to play with, this makes total sense. If I move it around or just tap it, look at how much the low frequency reeds get excited. I can only imagine how useless they would get at even lower frequencies. Just a massive noise from every stray vibration in your environment. But that said, I'm pretty impressed with how precise it can be. I can tune the CVT on the mill to lie between two reeds and see almost no excitation of either of them, which might limit its usefulness a bit, since you can't always adjust the speed of the thing being measured. So if it happens to fall between two reeds, you might not be able to measure it at all. But it's still a supremely pleasing little device. Analog, yet truly solid state, and yet also digital, at least in the sense of being quantized. I also found this interesting little oddity when poking around the listings, literally mint in box from 1952. It's another resonant reed device, but in this case it measures the frequency of mains electricity, with two sets of reeds centered on 50 and 60 Hz. At first I assumed there would be a little synchronous motor or solenoid in there to generate the vibrations, but looking at the patent, it actually excites the reeds directly using a magnetic field generated by the AC current. And it totally works, with a very fast response to both turning on and off the current. Here it is again in slow-mo. It's such a lovely thing. Maybe I'll build a little mounting box for it. So, that's a quick tour of the world of tachometers. I'm really glad I had this excuse to play with them all, but truthfully, for what little tachometer needs I really have, I'll probably just use the stroboscope. It feels nice in the hand, you don't need direct physical contact or need to put a retroreflective sticker anywhere, and it's nice to have control over the entire process. Plus, you know, rave gun. The next video really, truly should be that stained glass globe project I've been working on for like a year now. I've been making actual progress on it the last few weeks, and it's looking good. Look for that video by the end of the year, hopefully. And until then, cheers.